Alright, so this is a shell written in C, and I don't mean the shell that the project is running in, I mean the project itself is a shell. So this is a great way to learn fork, the exec functions, waitpid, all the tags that go along with all of that. And that's very useful if you're designing really anything that has to do with multi-programming, multiprocessing, really just anything that has to do more than one thing at once. This is a great way to learn it because you can't do it without it. So without further rambling or anything, we'll test just a proof of functionality with a basic command. So we'll just, I have to actually click out of OBS back into the window here. We'll just ls, it lists all of our things there. Cat readme. I'm surprised it's actually tabbing. That's interesting. I thought it would there. There's the readme. If you're interested, you can pause or anything, but yeah. Anyways, so as if you pause there and read that, you know what we're gonna get into. But so the next type of thing you can do is you can add arguments to your command. So instead of just ls, which once again lists the files in the current directory, we will do -a and the more detailed -a-l. There you go. Next, we can do, so real quick, we'll list the files again. So we have readme.txt and 352 shell.c. So, alright. So as you can see here, we have 352 shell.c and readme.txt. Those file names are important here. So we're going to move on to piping. And piping is this symbol here. For those of you who don't know, we're going to be using it to redirect the output of, I just realized we're in a terminal, we can't redirect. So the output on this side is going to be piped into the input of whatever we put on this side, right? And this will tell us error. Because we just try to pipe two things that don't actually exist. But anyways, so we'll do that ls command, which should give us this. But we're going to pipe the standard output to the standard in of the grep command, and we'll do grep text. So this should show us the results from here, but anything that has the text extension there. So this should just show us the readme, which it does. Same thing if we were to do C, or say if we just did -n2, then it just gives us two of them. So that's useful for all kinds of purposes, but that's not necessarily the purpose of this video. So next we have ones that were, so we have redirect standard in, which was somewhat touchy to implement at first because I was still kind of, this was one of the first things I implemented, so I was still learning my way around it. So and then redirect standard out, and I really hope I didn't mix those up, but I don't think I did. So what that means is, like I said, you take the standard input, which is typically this line. So if I do this, which is the different order than we did it last time, but it still works, then our standard input to the program is this. So this is what we're telling it to run, and these are arguments, and it's taking standard in from this command line. Standard out is when I run this and it prints these results. Its standard output is the shell. or the terminal, or printing to the user. So now we can say ls-a-l. So let's just do ls, mostly because I don't want to keep censoring. You know what? It's not a big deal. It's not a big deal. I'll just keep censoring my name or whatever. Not name, but my server name, so I'm running this on a server for ease of running the Linux commands. Because when I run it on my local machine, I have a Windows, so the Linux commands kind of fight with it. So we're going to redirect the standard output of this command to, we'll say, out.text. And now we don't get any output, but if we do ls, then we can see that there is now a file called out.text. And real quick, just for the sake of hammering home an example, if we do grep text again, now we get both of them. So now, instead of clearing, actually, also this is the prompt telling you, if you didn't pick that up, this is the prompt saying to, no, that's the new line. Now for proof, we will cat, which is open, well, not open, but you get what I mean. Cat out.text, and there we go. That is the output that should have been printed by this, but instead it is inside this cat.text file. That's pretty cool. So we'll clear, and now just for proof that we can make a file, actually. So once again, here's our file list. So let's touch. We'll just call it in.text for simplicity. Now we have a file called in.text. Echo a. Oh, I'm dumb. Echo a into in.text. Echo q into in.text. Echo g into, we'll just put like one or two more. B into in.text. I know there's easier ways to do this, but whatever. And echo. I think this will actually put the quotes in there. I don't need that. We'll just see what it does with that. I mean, it'll sort it by the F, but it'll be interesting, I guess. Okay, so now, once again, we will open in.text, and there's our, here, I'll make it a little easier for you to see. Also, once again, all these clear commands and everything are running in my shell. So I'll kind of get into the nitty-gritty about how that works later. I haven't used that figure speech in a long time. So we'll cat in.text, and there's that file. So right now it is A, Q, G, B. It's in a random order. So we're going to sort it. So if I were to just sort, it's gonna run forever because I didn't give it anything. So it's waiting for the argument, and there is no argument, so it's just gonna go. So we'll clear. I just kind of spoiled something there as well. But we'll sort, provide it input from in.text. And now there's the sorted in.text versus the unsorted in.text. So what we did was sort, redirect standard in.text. So it sort, and then we passed in that file, it read it, and turned this into that. So those are the three general things that this shell is implemented, aside from just all basic commands like that. Obviously there's stuff like sleep, which just 1, 2, 3, 4, 5, yeah. So that's kind of a boring one, but it will be important later. So now I introduce this program by saying multiprocessing, and more importantly, learning how to do background processes. So if I were to do ls illicit, if I were to do ls ampersand, then, well, this is a bad example because this command is going to run very quickly, so it's gonna, but I'll be able to talk you through it, I guess. So it ran very quickly. So this is normal, by the way. This happens in normal bash as well. So what happens here is I type ls ampersand. Ampersand tells my shell, okay, we run this in the background, which means typically if you run a program in the, or a process would, actually the process calls the program with the exec function, but once again, we'll get into that. If you run this with the ampersand, the child process runs this. The child process runs what you tell it to, and the parent process continues on through the loop and waits for more input. And that's what this is. The parent process is saying, okay, we're ready to take another command, and then because I used a really small example for the sake of explaining the setup, the background process finished quickly. So, but yeah, it's kind of cool. This right here is the shell assigning the process a number, which is 2. And then this is the process ID of the process. I don't assign that, obviously. The reason this is 2 actually is because we terminated that sort example earlier, and we'll get back to that, but that was put on the job list at task 1, and we'll explain that later. But right now, despite the output being printed in front of our prompt, we can still just do that, and then the loop will hit and it will tell us that our background command is done. So, which you think is useless because it printed it, but not all background tasks are going to produce output. Like if you redirect something, say if I did that, it gives me the process ID, and then I want to know if it's done. You know, I keep messing around, and then it says now it's done, and it says done in the command, so you know, oh, this is the one that finished. So yeah, this is, you're gonna be able to do the same thing you did on everything else, just in the background. ls grep text, run in the background. It's gonna execute quickly because it's a big command. But the best way to do this is show you, we'll do sleep 10, because that's gonna run a while. So sleep 10 here, we're gonna wait an entire 10 seconds. We're just gonna sit here. There we go. That is what sleep 10 does. But now if I do sleep 10 ampersand, it says it's running, it runs in the background. I can do whatever I want. In the meantime, I'm just gonna keep spamming ls for the sake of example. And there we go. The sleep finished in the background. I wouldn't have known that otherwise. And it tells me, hey, it's done. So that part was actually really fun to implement. I think that's really cool, and that's where I think a lot of the valuable learning comes from, just really handling where processes are and presenting that to the user and making it a clear, concise format. So now we get into why that first process was labeled number 2. So when we run sleep 10 and we don't want to run it, we ctrl-z and it stops. It's similar to if I were to press ctrl-c right now, which I'm not gonna lie, I did on accident earlier in the video, and that's why one of the cuts in this video is there. But it stops the command. But if we want to see the command, we can hit jobs, and here we are. So there's that first command, which is that sort that we killed earlier, and then here's that stop sleep 10. Now if I were to run a sleep 100 in the background and then do jobs, it would be here and tell me it's running. But you're probably wondering now, you know, what is the, I mean, we can't, the sort is just kind of a broken command, so we can't really do anything about that. But you would never actually put that in. I just put that in for the sake of the example of the broken command input. But we have this stop sleep 10 here, and it's not really, let's make sure that sleep 100 is still going, yeah. It's not really useful to us there. So why would I present the information to the user? Well, if you type background and then 6. So background and then this ID here. Now if we do jobs, we see that the sleep is running again. So we just do ls a couple times and there we go. So sleep actually, yeah, I'll actually display that real quick here. So sleep, that works as you would assume. It pauses it sends, so I don't really want to get into an OS lesson here, but basically things send interrupts to the scheduler, and the scheduler can say like, okay, you're taking too long, or okay, we're just going to move you, depending on whether you're doing something like FIFO structure or first come first serve rather, or something like where you're based on time slices. It all depends. So we're sending a signal to it to tell it, hey, just stop. We're sending it sig kill, which is a signal that doesn't really participate in some Windows terminals, so you got to get a Linux supportive one. Sometimes. The one I was using didn't, but it depends. So, but most good C terminals will work. I don't mean to scare you or anything. So anyways, C environments and compilers and stuff like that. So anyways, we send it a signal saying stop. That doesn't kill the process, although real quick we can actually do that. Alright, so I wanted to give an example of that kill that I mentioned real quick. So we sleep 100 background, we're going to kill, sorry, process 2598936, and then ls to get the loop to go again. And instead of saying finished or complete or whatever, done, that's the word, sorry, I was cycling between done, complete, finish, and then I settled on done just because it seemed simpler. So it'll tell you terminated sleep 100. So I forgot for a second there if I had to put in the shell number or this. I couldn't remember if I kept the normal kill command, which takes the PID, or if I made a custom one that needed that. But no, I kept the PID just because that is the normal one, so it's better to go with what people will know and understand to be more user friendly. So yeah, that's really cool. I like that it has not only that it has the functionality to do things like that people are typically comfortable and familiar with, but it will alert you. Instead of just saying it's done, it'll specifically say terminated. I'm getting errors because I'm pasting that terminated in there because I apparently accidentally copied it. So another thing of that sort, before we get back off of this little sidetrack train of thought, because that's how my little ADHD mind works, we will do, I guess this, no, we won't use the same one, that would be boring. We'll do a different one. So if I were to we'll just put in gibberish, right? This should give us an error which says, exec VP is the family of commands we're calling, so that's an error because you're telling it to call this, which just doesn't exist. But if I were to instead put in a real command, but put in arguments that don't exist, it gives you, the actual error information. And that's because the child process is really calling this program, and that program's output is going to give you this information. So even though this shell is my program and it's not necessarily a true terminal shell, it is going to give you this real useful output. And also, if for any reason your program terminates with invalid error or invalid response or an error code, it will come back to you and say something along the lines of finished with, or like exited with exit code 1 or 2 or whatever, and it'll present to you the error code. So we'll see if I can try to trigger that now. So we'll do sort and then a file that does not actually exist. Sorry, I forgot I set up a catch for that. I think too much ahead for these situations. I like bug catching, what can I say? And case catching, so programs aren't ugly and crash for users. But anyways, back to the main train of thought that we were having. Okay, so before that little side lesson on kill and error reading, we were talking about background processes. So once again, we'll set up that situation again, sleep 100, set it up in the foreground, kill it, jobs, there it is with our broken sort. And if we want to restart it, we run background 11, and there it is. So once again, the reason this works is it sends the stop process rather than a kill process, and that once again just stops the process, obviously. And then you send, when you hit BG11, you send kill stop sigcont or something. Yes, that is it, sigcont, which is a dangerous thing to say on YouTube. But that sends the signal to the process to continue. But the reason, if I hit LS right now, it'll continue going. But if I were to, can I get the, yeah, but it stopped quicker than you would imagine. Or actually, sorry, I read stop sort. So it's gonna keep going for a while. But if we were to run a sleep 10 background, and then, or rather sleep 10 foreground, cut it, and then you'd think it would be stopped, but if we wait, you know, a couple seconds just talking here while I stare at the counter just to kind of stall just long enough for this example to work. If we do jobs, it is stopped. That background sleep's gonna be done here soon, and then it's off the list. Oh, jobs, plural. That's off the list. So that that job is stopped. That sleep 10 is not running. I promise you that sleep 10 is not running. But if we were to, I don't know why it cleared, I don't remember its ID. But if we were to background 13 and resume it, then ls, it's done already. So that's just because sleep runs on clock time, not execution time. Sleep, the command itself, doesn't save the amount of time it has been running. Rather, it compares, oh, I was started at this time, and now it's this time, I'm supposed to be done. So it does work. Sleep is an easy way to display that, but I just want to explain that one little caveat, and that's why sleep is stopping and claiming to be done so quickly, is because, well, it is done so quickly. And this line, lastly, will contain the entire command line argument, aside from, I have it ignore the ampersand saying run in the background, just because it makes the formatting cleaner. But yeah, that is the shell. If anybody would like an explanation video on fork, exec VP, I like that one more than its exec VP, which is what I'm saying. It's kind of hard to actually say that. And then there's exec LP, I believe, which is the other one that I tried to use, but VP worked better for what I was doing. Fork is obviously the thing that creates the child process, and then to handle the processes, you use waitpid or just wait, but PID allows you to have, I keep forgetting you can't over, allows you to have stuff like this. Is it WH or is it just W no hang? Something like that. And W no hang is what waits but doesn't stop the command line, and that's how you run stuff in the background. And I would love to make an explanation video on this if there's anybody out there who's interested, because there's not very many out there, and those that are very convoluted, so I think a very straightforward and quick basic explanation video would be helpful to people. So if that'd be something anybody's interested in, I guess comment, but otherwise this has been the functionality demo of my shell project.